Hello, AP Chemistry students. Oh, look, it's our favorite spider. He's so cute. Hee hee hee. And this obviously is not what we're talking about, but this is what you can do with a scanning electron microscope because electrons have such a tiny wavelength. They can bounce over surfaces and you just can get amazing resolution. Way better than you could with a normal microscope. But we'll say goodbye to our little spider friend. And today's topic, and by the way, this is the last video I will do for chapter 7, is about quantum mechanics. So electrons do behave real strange on the quantum level. I mean, they have a measurable wavelength, but they also behave like a particle. So scientists put this whole weird behavior of electrons into this idea known as quantum mechanics. All right, so the basic premise is very simple, and you're already familiar with it. From last year chemistry, when we first learned about energy levels, we thought, oh, it's like this circle, and the electrons sort of run around as if they're in a hamster wheel. We concluded that this is not how electrons behave at all, that this is the wrong way to visualize electron movement. And then we came up with this whole idea, which we called the electron cloud model. Yes. And so basically, all these little dots, okay, the more concentrated the dots are, like here in the middle, there's a much more probable chance that you're going to find an electron in this area than as the distance goes further from the nucleus. So then we just sort of put a circle around it and say, you know what, that's an orbital. Someplace in that space, you're going to find that electron moving. Okay. But how did this come to be? And the basic premise is electrons are weird. So, I mean, if you think about it, an electron has a distinctly measurable wavelength. So, if you have an electron, where is it? If it's behaving like a wave, it's kind of like the light that's filling this room. Is it here? Or is it here? Or is it like throughout the space? You know? So, that's where Heisenberg uncertainty principle comes from. Uncertainty principle, which basically, we got problems here. Principle. I think I spelled that very wrong. Okay. Like there's an N in there. But bottom line is you can't know the location and the speed of an electron at the same time, which kind of makes sense because if you were using some kind of instrumentation and you actually want to know where an electron was, you'd have to stop it from moving for that 1 second to know where it was. Well, then you wouldn't be able to know its speed at that particular moment at the same time. And likewise, if you had some kind of instrumentation where you could know the speed at which the electrons are traveling, well, then it's going to be showcasing its wave-like behavior. So where is that electron? Is it there? Is it there? I mean, if it's behaving like a wave, it's kind of throughout this region. So it gets really confusing. So it's not really a limitation of technology. It's just an acknowledgement that, yeah, electrons behave really strange. So we're going to accept the Heisenberg uncertainty principle, and we're going to accept that there's these orbitals, this region where electrons will be found somewhere in that space. Now, the funny thing is, how did we come up with these shapes? Believe it or not, that's where math comes in. So a gentleman by the name of Erwin Schrödinger spent his life solving and developing wave functions. So if you're really good at math, knock yourself out. See if you can solve this very simple wave function. Okay. But for our purposes, we're not going to worry about the math. Okay. But just understand that it's math that got us to understanding what orbitals, what the shapes look like. Okay. I know right here you might be intrigued by the fact that it says better cat video. We will watch that video in class. And it's just a brilliant analogy that Erwin Schrödinger came up with that has to do with cats and poison, and you will find it interesting. So we'll watch that in class. Okay, and last but not least, of course, we know that an orbital represents a region where you're going to find an electron, but that same orbital also has a certain energy. So electrons can only have distinct energy quantities, okay? And just to give you an idea how that works, that's what this picture is trying to illustrate. That if electrons behaving like a wave, if you have a wave, and let's just say it's going around the circle, which is not true, like this is a bogus simplification of how electron behavior is. But if you have this wave, if it's the perfect distance away from the nucleus, or if that electron is a perfect energy, then that wave kind of fits perfectly around the circle, okay? And that energy for that electron is allowable. But if you look at this one, so this electron has an energy that's not favorable because when you go around that circle, it doesn't match up perfectly, so that wave sort of ends up canceling itself out. So this is not going to work, okay? So again, the whole idea is that in an orbital, the electrons will have a certain energy, and electrons can't have energy that's in between energy levels, okay, as we've talked about before, okay? So this is great stuff. I hope that in the textbook, you do take the time to read the little segment about quantum mechanics. This one's an even shorter version, but I think the book does an excellent job because I can only give you the cliff notes. Okay, it's a brilliantly written story, and there's a lot of historical figures that come into play, and I do expect you guys to read that part of the book. Okay, but you don't have to solve wave functions. That's good. And speaking of Heisenberg, of course, Werner Heisenberg spent his life trying to unravel the mysteries of electrons. But if you look up Heisenberg on the internet in today's day and age, well, this is the Heisenberg that comes up. And of course, that's Walter White from the famous series Breaking Bad. So it was funny. It took me about 3 screens of these type of Heisenbergs before I got to the real Werner Heisenberg, and it would happen to be this picture, which I found comical because that's probably how he feels with all this attention to his name in not the most positive light. Oh, that was a really good series. And then also there's a whole litany of jokes too about not being able to know the location and the speed of an electron. Like this one's my favorite. No, officer, I don't know how fast I was going, but I do know exactly where I am. So you guys could try that line maybe if you ever get pulled over or something like that. Who knows? It might work. Or they say by his grave there's some kind of sign that says, "Here lies Heisenberg." Maybe. See? So the poor guy. But nonetheless, we'll move on. So what's the application of all these orbitals? Oh, and by the way, I should say that quantum mechanics is awesome, but where this leads in modern day time is you guys could look up stuff like string theory and whoo, the quantum world even gets weirder when you talk about some multiple dimensions and things like that. But we'll leave that for another day, maybe after the AP exam. So for our purposes, we were going to trust that scientists were able to solve those wave functions and they were able to devise these orbital shapes. Okay, and you remember this from last year. There's different orbitals with different shapes. So the simplest one was the S sublevel, okay, which is spherical in shape. It's just a big old ball or circle, okay, and there's one type of S orbital, just this round spherical shape. And then p orbitals, okay, and I don't know, some people say figure eights. I think your textbook uses the term dumbbell shape. Okay, so we call this, these are each lobes. So keep in mind that the orbital or quantum mechanics would say that somewhere in this region you would find an electron. So is it necessarily here? Is it necessarily here? Or actually that electron, if it's exhibiting its wave-like behavior, would be in both lobes at the same time, if you can imagine. But nonetheless, there's 3 different types of p orbitals, and it's just about orientation. One goes along the x-axis, one goes along the y-axis, which is coming out of the paper and going back into the board, and then you got one along the z. So it's just different orientations, but they all look the same. And the D, and by the way, I'm changing this to sublevel. Okay, so all 3 of these together represents the p sublevel. Okay, and then each one of these is a p orbital. Do you see the difference? So the D sublevel, well, let's see. So now we went from 2 lobes to 4 lobes. And then this weird one, which is kind of like, I don't know, I always call it the donut shape. Okay, so the D sublevel is, we'll just go with clover, because most of them have those 4 lobes, and then plus the weird one. And there's 5 different types of d orbitals. And just again, math predicted these shapes. Those wave functions predicted that an electron will be found with a certain energy, would be found somewhere in this region. And then the f orbital, whoa, never really talk about f. And in terms of what are we going to call it, we'll go with complex. How does that sound? So the f orbitals are complex in shape. I would never in a million years ask you to draw these or even recognize them, except that they go from simple to more complex. And I think you guys are following the trend. 1, 3, 5. There are 7 types of f orbitals. So all of them together is the f sublevel. Yes, but there are 1, 2, 3, 4, 5, 6, 7 distinct f orbitals. Okay, and let's see. You guys probably remember that how many electrons can you fit in each one of these orbitals? You can fit 2 electrons, 2 electrons, 2 electrons. So you can fit 6 electrons in total in the p sublevel. 2 electrons in total in the s sublevel. And then 2, 4, 6, 8, 10, 10 electrons in the d sublevel. And you got it, 14 electrons in the f sublevel. All right, good. So now we're going to put these all together. I don't know if your teacher showed you this last year, but this is called the Aufbau diagram or Aufbau principle. And the basic premise is that electrons, when you put them in the orbitals, they're always going to start with the lowest energy, and they're going to work their way up to the highest energy. So you guys remember that you had those energy levels, right? These guys. anything that's in the first energy level is lower energy than anything in the second energy level, and then the third energy level. But there is some overlap, so we're going to see where that happens. So overall, lower energy level N means lower energy, but there is some overlap. So here's the first energy level. Here's the second energy level. So that would be in the second ring, that there's 2s sublevel and a 2p sublevel in the second energy level. Okay, so then you come to the third. So 3s, 3p, 3d. Now you might be seeing a connection here, that if you're in the third energy level, you can have 3 sublevels. 1, 2, 3. If you're in the fourth energy level, you can have 4 sublevels. 4s, 4p, 4d, 4f. And that continues, okay? But what you guys notice is there's some overlap. So here's my third energy level, but all of a sudden the 4s comes in before the 3d. And the reason for that is it has all to do with shape. Okay, so we'll say the 4s is lower energy than the 3d. It's all about the shape. So a 4s or any s orbital is spherical in shape. So the electron density or likelihood of finding an electron will be somewhere in the middle here. The closer you are to the nucleus, the more favorable, okay? Whereas if you're talking about the 3D, that's going to be one of those weird shapes that look like this. Where's the chances of finding the electron? Is it close to the center or is it like far away from the center? Okay, and with these weird shapes, what happens is the electron density is further away from the nucleus, and that's not as stable. So bottom line is S sublevel always has lower energy than the P, than the D, and so on and so forth. So you actually see some overlap because the 4S having that more favorable shape is actually lower energy than the 3D because of the electron density being away from the nucleus. Okay, does that make sense? All right, so I'll just put a little hint to you that when it comes to this order, it's all about shape. Okay, and then you got that overlap. But the good news is you don't have to memorize any of this because, as you probably recall from last year, it's all built into how your periodic table works. Okay, and this is about where I think you guys can sort of fly in your own wings because I bet you guys remember a lot about how to do electron configurations. The only thing I'll remind you about is that on the far left of the periodic table, that's the S block. Okay, and then you had the P block on the right-hand side, the D block's in the middle, and then the F block is your lanthanide and actinide. And just remember, the first row, that's like the first energy level, okay? And since it's the first energy level, you only can have one sublevel, so that's 1s. Okay, so 1s1, 1s2. And then when you go to n equals 2, the second energy level, you can have 2 sublevels. So you have the 2s, and then you cut across, and you have the 2p. And the 2p sublevel, of course, has 3 orbitals, so it can hold 6 electrons. 1, 2, 3, 4, 5, 6. Kind of remember how that works? And then n equals 3, so you got 3s, cut across, 3p, okay? And then there's that overlap. So actually 4s comes next, okay? And then the 3d comes in order. So, but you guys can just totally just read this off your periodic table. So this is the fourth energy level, so 4s, but the d will always be 1 n energy level lower. So 4s, then 3d, and then back up to 4p. The s and the p are always linked. Okay, they're always going to be in the same energy level. Okay, and then same thing here, 5s, go 1 down for the d, so that's 4d, back up for the p, right? But here's where things get interesting. So we're in the 6th energy level, so that's 6s. But then if you guys remember, if you look at your numbers, that's where the lanthanide series comes in. Okay, so 6s, this is going to be 5d, but then for the F, you're actually going to see that they're so unstable that that's going to be 2 energy levels lower. So 6s for the, sorry, that's F. For the F, that's always going to be 2 lower, and then back up to the D. Okay, and 6p. And the same sort of trend is going to continue here. So 7s, and then you come down here, and that's going to be 2 lower, so that's going to be 5f, and then come back up to the D. That's going to be 60, and then back up 7p. Now, if that seems confusing and you've kind of forgotten how that works, just come talk to me and we can walk through it, okay? From here, I'm going to let you sort of figure these out on your own, okay? Don't forget that orbital diagram is when you guys do the up and the down arrows, okay? And then the electron configuration looks something like this. 1s2, 2s1, okay? Meaning 1 electron in that second energy level, okay? So I'm going to suggest that you guys go through and do these and check the key on Schoology. And do remember that there's a couple critical rules. Pauli exclusion principle, basically no two electrons can have the exact same location, okay? So in one orbital, the electrons have to have opposite spins. So when you fill up an orbital, whoops, I go back this way, just like we did here, one goes up, one goes down, okay? So that's Pauli exclusion principle. And then Hund's rule basically says electrons spread out before they start pairing up in an orbital. So what that means is when you're doing oxygen, so we got 8 electrons to account for, so 1s2, 2s2. When you go up to the 2p, you're going to keep those guys spread out according to Hund's rule before you start pairing them up. Okay, so then to get our 8th electron, 1, 2, 3, 4, 5, 6, 7, then we start pairing up. Okay, and then you got to fill this sublevel before you go on to the next. So that's Hund's rule. When that comes together, 1s2, 2s2, 2p4. Okay, and that's it. So the last piece, since this is a great example, is don't forget what valence electrons are. So when you look at this, which ones are the valence electrons? Always the ones in the outermost energy level. So that's the 1s2, and then the 2s2 and the 2p4 are in the outermost energy level. So these would be the valence. All right, as you guys go through, there'll be some interesting things that happen with ion charges and noble gas configurations. And there's a couple exceptions. And you guys should be able to find this stuff in your book and just work through it. Make sure you check the key on Schoology really, 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 really thoroughly. Okay. Some more terms. And then last but not least, at the very, very end, there's a little history review. I think you just need to be just loosely familiar with these guys, okay, and what their accomplishments were. All right, please do not hesitate to come talk to your teacher if you have questions about any of this. If there's stuff that you really don't remember from last year, we would love to help you. All right, good luck. Happy Chapter 7 studying. Thanks very much.